Let's use limit comparison for the sake of argument, and then we can talk about whether or not just the comparison test would work. So the sum n equals 1 to infinity of 1 divided by n times the square root of n to the 6th plus 1. All right, so again, we think of this guy as an. And if we want to use the limit comparison test, what trick could we use here for finding our bn? Well, it is kind of the same trick. Okay, remember what the trick was in the last problem? If it's a rational function, if an is a rational function, to construct bn, we take the highest power of n in the numerator, highest power of n in the denominator. Well, numerator is just a 1, right? So if I want to construct my bn, so this again is step 1. If I want to construct my bn, I'm just going to, well, it's the highest power of n is essentially 0, n to the 0. So just take the 1, take the numerator as is. Even though it's not a rational function, this will work. Look, in the denominator, if you delete that plus 1, you can get the exponent on the n. In other words, you can think of the highest power of n as n in the denominator as n times square root of n to the 6th. What's the square root of n to the 6th? N to the 3rd. And then what would you get when you take n times n to the 3rd? So n to the 4th. Okay, now we're still in step 1. We want to construct an over bn. Okay, so let's do that. An over bn is the original nth term, 1 over n times the square root of n to the 6th plus 1 over 1 over n to the 4th. Flip and multiply, get n to the 4th on top over n square root of n to the 6th plus 1. And then how does that simplify on top? Well, you got this n on the bottom, though. That cancels, right? So n to the 3rd on top over square root of n to the 6th plus 1. Okay. What's the limit of that guy? So I'll do this using the limit notation. The limit as n goes to infinity of n cubed over the square root of n to the 6th plus 1. Okay, you could look at the related function and use L'Hopital's rule, but don't do that. I don't want you to forget these limit tricks that you learn, especially when L'Hopital's rule doesn't apply. So what was the technique in Calc 1 you would use? If you take, how about the highest power of n in the denominator? And you have to take into account the square root. Now, it's not okay. You can't rewrite this as the square root of n to the 6th plus square root of 1 in the denominator. You can't do that. But when coming up we're trying to evaluate this limit, and when coming up with a technique for doing that, we want to multiply numerator and denominator by something so that we get a limit we can evaluate. And the trick, when it's just a rational function, is you play with it, and I think the rule is, I usually play with it to figure it out, but I think the rule is if you take the highest power of n in the denominator, multiply by 1 over that numerator and denominator, you'll get nice things to happen. So what's the highest power of n in the denominator? Well, okay, it's not obvious because it's not a rational function, but since it's the square root of n to the 6th, we kind of think of it as n cubed. And so if you multiply by 1 over n cubed, numerator and denominator, I think that'll get you where you want to go. So look, in the numerator, if you multiply those guys, what do you get? You do get 1. In the denominator, you have to bring this guy inside the square root, which means now this is a good trick to show you because it comes up from time to time, and you've seen it before, it's just been a while. If you bring a number inside a square root, what do you have to do? So you don't change the value. You have to square it. So that if you bring that inside, you get the square root of, okay, in parentheses, n to the 6th plus 1, times the square of 1 over n cubed. 1 over n cubed times itself would be 1 over n to the 6th. Like that, which is the limit as n goes to infinity of, okay, in that radical, underneath that radical, distribute the 1 over n to the 6th. What do you get? 1 plus 1 over n to the 6th, right? And now you can evaluate the limit. And so what, okay, individually you can take the limit of a constant's a constant. We know the limit goes inside continuous functions, so we can bring the limit inside the radical. And individually take the limit of 1 plus the limit of 1 over n to the 6th. What does that guy go to? 0. So you get 1, as the limit, for the limit you get 1 over square root of 1, which is 1. Okay, so hold on a second. Let's finish the idea here. We have to show that this limit, an over bn, is positive, right? So you should make note of that. And then that's, by the way, that 1 is your L from the limit comparison test. So you're done with step 1, which is the hard part. Step 2, okay, you should already know what's going to happen. You're going to take the sum of what? N equals 1 to infinity. The simpler function. What does that do? Converges. Why? Yeah, it's a p-series. P-series, p equals 4, which is greater than 1. So what's the conclusion? Okay, so writing down the original series, this guy converges because we know from LCT it's going to do the same thing as the sum of the bn. And so I'll just say converges by LCT. So once again, it's the first step. It's a little sticky. The first step's a little sticky. The next two steps look exactly the same as the comparison theorem, which is good and bad because then you might mix up the two, right? Now, my question is, could we have used the comparison theorem on this? Let's make sure. If you were going to use the comparison theorem, you would take the an, do it in orange. You would take the an, actually, let's compare with the comparison theorem. So step 1 of the original comparison theorem, you would just write down the given nth term formula without the summation notation. And then what would you do? How would you get the simpler function? It would be a process that looks similar to what we did in some of this first step. Well, we know what happens if we eliminate the plus 1, right? Does it become bigger or smaller, the overall value? You're making if you eliminate the plus 1, are you making the denominator smaller or bigger? Bigger. Denominator. Smaller, right? If you eliminate the plus 1, which makes the overall guy bigger, which I think is what you meant. So that's less than 1 over n times square root n to the 6th. Would you agree? And then, okay, if you simplify that, what do you get? 1 over n to the 4th. And then they're both bigger than 0, right? And then you know what's going to happen right now. What does the sum involving 1 over n to the 4th do? Converges. So what does the sum of the original series with smaller term do? Converges by comparison. Oh, the comparison test would have been easier on this one. So you might think, well, why would I ever use LCT? Here's the thing. There's going to be times when the limit comparison test will work. The comparison test won't. You'll see, and all else, I won't show you an example except to say that you'll see an example in the homework. Maybe more than one. Okay? So my suggestion is this. If you think comparison is going to work, try the comparison test first. If that doesn't work, try limit comparison.